this video series on list-based data structures. In this first part, we'll give an introduction to array-based list data structures, designing, refining, and testing a basic Java implementation. As you've probably experienced, it's rare to deal with only one piece of data in a program. Instead, it is usual to store multiple pieces of similar data in a collection of some sort. Many languages usually provide support for this via arrays, either dynamic or static. Java, for example, has dynamic arrays that can be initialized using the new keyword. But as you've also probably experienced, arrays are not an ideal solution in many cases. First, the capacity of an array is fixed when it's created or allocated. You cannot dynamically change the size of an array in many languages without manually reallocating new memory and copying the array contents. Moreover, we may not know how big of an array we need, or we may not need its entire capacity at a given point in the program. If we wish to remove or shuffle elements, it may result in holes in our array of non-contiguous data. All of these problems can, of course, be easily handled if we take care. The problem is that all of this manual bookkeeping falls to us to take care of it. We have to worry about all of these details at every point in our program, which can be very complex and error-prone. A better solution is to use a list data structure that encapsulates all of these details inside the data structure itself. The basic functionality that a list provides is the ability to add elements, retrieve elements, and remove elements in some manner. The details of how each one of these basic operations are achieved are encapsulated in the list data structure, which includes automatically resizing the list's capacity as needed. This allows us to simply use the list data structure in an abstract manner without having to worry about all the details. How exactly elements are added, retrieved, or removed are determined by how we design the interface in our list. That is, the public methods that we design for our list form the interface for how users will interact with our list. For example, to enable users to add an element to a list, we could allow them to append to the end of the list or to the beginning, or we could allow them to arbitrarily insert elements using an index-based insert method. In addition, we could design our list to have other convenience methods, such as determining the size of the list or batch operations to add or remove multiple elements with one method call. To demonstrate these ideas, we'll iteratively design and implement an array-based list data structure in Java. We'll design a list that uses an array internally to store elements, but which encapsulates the details inside of a class. As a first iteration, we'll design a basic list to hold integers and refine and improve it as we go along. I've created a new class called MyList. The first thing we need to do is design the internal state of the class. Since it's an array-based list, we'll need an array. We'll also need to keep track of how many elements are stored in the array. Java does allow you to determine the size of an array using the .length property, but this is not the same thing. The array could have a capacity of 100 elements, but we may only be storing 42 elements. To keep track of the size, we'll create another variable. Let's include a default constructor that initializes these two variables. We'll initialize the array to have an initial capacity of 10 and initialize the size to 0 to create an empty list. Now let's draft an initial interface to allow a user to interact with our list. I'll add methods to allow a user to add an element to the end of the list, remove an element at the beginning of the list, and to retrieve an element at a particular index. Let's implement each one of these in detail. I'll start with the easiest retrieval method. Given an index, it's easy enough to return the element at that index. However, we have to be careful, as the user outside this class may pass an invalid index, one that is either negative or that exceeds the number of elements in the array. If we left it as is, we would get an index out of bounds exception in these circumstances. However, that would expose the fact that we're using an array inside the class and we don't want any leaky abstractions. Instead, we'll check for these conditions ourselves and throw a more appropriate exception. Now let's implement the add to end method. The first thing we need to do is to take care of the situation where we may not have enough room in the underlying array to fit the new element. Let's write some code to create a new, larger array, copy over the old array, and make the lists array refer to that new copy. With that taken care of, we can unconditionally add the element, making sure that we keep track of the size variable. That's pretty good, but we can improve this code a little bit. Following the do not repeat yourself principle, we can leverage the functionality that Java provides in the array class to simplify our code. That's better and likely more efficient too. Now let's finish up the last method using the same basic ideas. One corner case that we may need to handle is when the user attempts to remove an element from an empty list. Consistent with the previous methods, we'll throw an appropriate exception. With the add to end method, the return type was unused. With this method, we could redesign our method to provide a more useful functionality by returning the element that was removed. The user still has the option of ignoring the return value, but returning it provides more general functionality. Another thing to notice is that we've hard-coded the value 10 in several places. I'll improve the implementation by moving it to a static variable. Now let's test our implementation to ensure that it works. To do this, I'll create a demo main method that creates a list and adds some elements. I'll also include a toString method so that we can verify the list contents. When we run this program, we should expect that the list grows with elements 10, 20, 30, each appended to the end of the list. And it works. We can then run this in reverse, removing each element until it's empty. We can also test the expected behavior of throwing an exception by asking for an invalid element. Looks like everything works. However, this sort of testing is more ad hoc testing, and though it provides some assurance that our implementation is correct, A much more formal testing approach should be used in practice using a testing framework with many more repeatable test cases. That way, as we make changes to our implementation, we can automate the process of testing and re-verifying. There's still a major problem with this implementation, namely that this list can only hold integers. If we wanted a list to hold doubles or strings or some other user-defined type like a person class, we would need to essentially repeat the implementation for each type that we wanted to use it on. This is not an ideal solution. Instead, we want to be able to write one implementation that solves this problem for any type of list. This is a quintessential example of when you would want to use parameterized polymorphism to create a generic implementation. In the context of Java, this means using generics. I've created a copy of our implementation, saving the old version. We'll start by parameterizing the class using the meta variable t. We'll now modify the underlying array to use this type of variable. We'll now modify the rest of the methods, replacing the integer references to our type variable. We've already hit a snag in the constructor. Java will not let us instantiate an array with a generic type. This is because different types require different numbers of bytes. For example, a primitive int requires 4 bytes, while a double requires 8. The number of bytes that an object reference takes can even vary among different JVMs. Thus, the compiler has no way of determining how many bytes would be needed to be allocated for the instantiation. Instead, we'll use a raw object type and force a typecast. Now let's change all the other references as well. Let's compare this implementation with our original. As you can see, we never really used the fact that the original implementation was storing integers. The only difference is that we've removed the particular type and made them more generic. Now our implementation will work with any type, strings, doubles, etc. This really showcases the power of polymorphism. We could improve our implementation further by adding more functionality and convenience methods. For example, we could add an isEmpty method. We could implement a generalized index-based insert method to allow a user to insert elements at any point in the list. We could add additional convenience methods to add or remove elements from the beginning of the list. Or we could implement batch methods to add or remove multiple elements at once. Or we could tune the sizing parameter that we had previously fixed to 10. We could even scale up by some linear function or double its size for geometric growth or do some performance testing to see what works best. I encourage you to implement all of these variations, but for now we'll focus on the index-based insert method. We'll start with some basic index checking. Clearly negative indices are not valid, but what about the other end? If the list had 10 elements with the last element at index 9, should we not allow the user to add an element at index 10? This would be equivalent to adding the element to the end of the list, so it seems that we should allow it. We'll reuse the resizing code from before to make sure that there's enough room for each element. Note that we're not really violating the don't repeat yourself principle here, as it's basically only a one-liner. If we were to split this functionality into its own method, we wouldn't really be reducing the amount of code. Next, we need to make room for the new element by shifting elements after it. Now we can add the new element at the given index and update our size variable. This almost looks complete, but remember we should thoroughly test our implementation. Good testing would cover all the possibilities, testing even the corner cases of adding to the beginning, to the end, and the exceptional test cases as well. Note that we added 10, then 20, then 30, all to index 0, resulting in 30, 20, and 10. Let's also test by adding at something to the end. Looks like everything works. Note that we have two methods that are strikingly similar: the add to end method and our new generalized index-based insert method. We can refactor one of these to use the other, simplifying our implementation and reducing the overall amount of code that we have to test, maintain, and worry about. In general, more specific methods should use more general methods, and so we'll modify our add to end method. There's a lot more that we could do here, but you get the basic idea of an array-based list implementation. In the next part, we'll look at an alternative list implementation that uses a series of connected nodes to form a linked list.